last year, you all spent some time graphing polynomials. Do you remember that? You found zeros, you talked about multiplicity, you talked about beginning and ending behavior, and you were able to roughly sketch a polynomial. However, you weren't quite sure where, like the actual coordinate in which that polynomial would switch directions, right? And we kind of told you to just approximate it. Once you get to calculus, you will know exactly where that happens. Okay. So what we're going to do is we're going to take all of our knowledge from pre-calculus, zeros, asymptotes, intercepts. We're going to combine that with our calculus knowledge, beginning and ending behavior, so the limits towards infinity and negative infinity, increasing, decreasing intervals, minimums, maximums, concave up, concave down intervals, points of inflection. We're going to put all of it together and make a graph without ever referring to our graphing calculator. Okay. So you'll notice we're spending the next 3 days on this. Today I'm going to walk you through some examples. You're going to try some in your homework tonight, and then we're going to just keep working on it. Okay? Every function is different. Okay? We're going to get some very straightforward polynomial examples. We're going to get some examples with asymptotes. We're going to get some graphs with corners. Okay? So before we move forward, what is going to be our clue that a graph has a corner? Well, no, absolute value is not the only function that has a corner. But what's true about a corner? Okay, the derivative is undefined. Okay, if we get an undefined derivative that is not an asymptote, we know there's going to be a corner there. Okay. All right, so if I ask you to sketch a curve, these are the items I'd like you to consider. What is the domain? Are there any discontinuities, really? Are there any asymptotes, okay, or holes? What is the end behavior? What are the intercepts? And then from yesterday's quiz, increasing, decreasing, mins and max, concave up, concave down, points of inflection. Okay, so each problem that you do, these are the sets that I want to see, okay? I've already uploaded my key to tonight's homework so that you can see exactly how I expect your work to look. Okay, yes, Calc is helpful, but I want your work to look a specific way. I don't really care for how Calc does these problems. So what we're going to do a very straightforward polynomial example, and then we're going to do an example with some discontinuity so you can see what it looks like. Okay, we are going to take our time, all right? So we might only get through 2 problems. That doesn't mean that your homework is going to take you 3 hours, okay? We're going to go slow in here. We're going to talk a lot about some things, but that's just a warning, okay? So go ahead and write this down. Q. What's the domain of any polynomial?
Negative infinity, positive infinity.
Good. All real numbers. Which is negative infinity, positive infinity. You can say it either way. Okay. If the domain was not all real numbers, then we would need to keep in mind which numbers not to plug into our function. Okay. The end behavior. Oh, I guess. Sorry. Are there any discontinuities, Austin?
No.
There are no discontinuities because it's polynomial. End behavior means what's the limit as x goes to negative infinity, and what's the limit as x goes to positive infinity. Okay. Remember, this is a polynomial. It looks like there's a positive leading coefficient, and it's an odd degree. Okay. So Isaac W. What is our ending behavior? Let's start with negative infinity, so to the left. Okay, and to the right? Good. To the right, it's going to rise. To the left, it's going to fall. Positive leading coefficient with an odd degree. All right, we're almost out of our preliminary stuff here. Our intercepts. Abram, how do we find a y-intercept? No, not necessarily. You can find either one of them first. Yeah. If we plug 0 in for x, what are we left with? So 0, negative 1 is our y-intercept. Okay. Now, if we try to plug 0 in for x, is this something that we can factor? It is not something that we can factor. Okay? If you have a polynomial that doesn't factor, it's okay not to find the x-intercepts. Okay? I believe on your in your homework you will be able to find x-intercepts. Okay? You'll see why here in a little bit. I don't want to make you do like the leading coefficient test. You remember that with the synthetic division and finding all the zeros? We could go through and do that. So, for now we'll just settle, okay, we're not going to find these x-intercepts, but if it was factorable, we would find it, okay? Or if it was a quadratic, we would use the quadratic formula, okay? So, let's talk about everything from our quiz yesterday. We can take the first derivative to determine increasing, decreasing intervals, as well as minimums and maximums. Okay? So, Josie, what is our first derivative?
3x squared minus 6x.
Excellent. Okay? So we need our critical points, which means we set this equal to 0 and undefined. Not going to be undefined, so we'll just worry about 0. Is there a GCF in this polynomial? We can take out a 3x, left over is x minus 2. Cole, what are our critical points? Okay. Logan, if I plug something to the left of 0, what does it make our derivative? Good. If we plug something between 0 and 2, Michael, what does it make our derivative? Awesome. And to the right of 2, Sammy. When our derivative is positive, Aaron, what does that mean about our function? If our derivative is positive, what does that mean about our function? What does the derivative tell us? Yes. So, okay, good. So here's where our function is increasing. Here's where our function is decreasing. Okay, so Joe, what's happening at x is 0? Okay. And Joe, what's happening at x is 2? Okay. So let's think about this information. We know that we are going to be increasing from negative infinity to 0 and 2 to infinity, and we're decreasing from 0 to 2. We have a relative max at x is 0 and a relative min at x is 2. Since we're actually creating this graph, we need to know these coordinates. Okay, so go back up to the original function. Madison, what do we get when we plug in 0? -1, we've already found that coordinate. Okay. And Madison, what about when we plug in -2 or +2? Excuse me. Okay. It is not. What is 2 cubed?
Oh, I totally did that one. -5.
-5. There it is. Okay. So we know that these two coordinates right here, we can plot, and that's where a graph has to switch directions following this information here. Now let's talk about concavity.
I got this.
Wait your turn. Isaac S. What's our second derivative? Great. To find potential points of inflection, we set it equal to 0. So Trevor, what's our potential point of inflection? Notice how I'm labeling my number line because now we have more than one number line in our work. Jake, to the left of 1 is our second derivative going to be positive or negative?
Negative.
And how about to the right? Good. So Gina, if our second derivative is negative, what does that tell us about our function? Good. We are concave down from negative infinity to 1 and concave up from 1 to infinity. Since we have a change in concavity, Larry, what's happening at x is 1?
Change directions.
how about on the function? What's happening when we change concavity? What do we call that? Good. So we have a point of inflection when x is 1. We plug 1 back into our original function. Josh, what's f of 1? Okay. Now we get to put it all together. Are you ready? We know exactly what this graph looks like because of all of this information. Okay. First, let's plot all of our coordinates. So our intercepts. We have an intercept of 0, -1. And 0, -1 was something else, wasn't it? It's a maximum. So I might just label max just to give me a reminder. You don't have to. Okay. We also had a minimum, right? Where was our minimum? Okay. And our point of inflection was 1, -3. Okay. Okay. We know from -infinity to 0 and 2 to infinity we need to increase. 0 to 2 we decrease. We're concave down until the point of inflection, and then we're concave up. There's our graph. Isn't it pretty?
So can you just do the second derivative test for when finding like the min and maxes? So if you already know it's concave up and down, you know it's max.
Right. Since you have to figure out increasing and decreasing intervals, you're already doing the first derivative test.
Well, I just did because I already know. If you know, we already know if you have a max, then that's going to be increasing to that point. Then it has to be when it's going to a min, it has to be decreasing to that point.
So you're saying you don't want to find increasing and decreasing intervals at all?
Well, like I find it, but like already know if it's a max, then it has to be.
Okay, so here's the thing with that. Not all critical points are relative minimums and maximums. So it would still be important to know where we're decreasing and increasing. Ladies and gentlemen, I'm answering a question right now. You may want to hear the answer. Okay. So Austin was asking if he could just skip over increasing and decreasing intervals and use the second derivative test and then just kind of know where we're increasing and decreasing. The problem with that is going to come in our next example when we have asymptotes. Not always will we have minimums and maximums, and so you're going to have to know the decreasing and increasing intervals. Does that make sense?
Yeah, but like just for a polynomial function, we would already know that there wouldn't be an asymptote.
Yes. If it's polynomial, what you does. Except if I specifically ask on the Quiller test to give me the increasing, decreasing. Okay. All right. Other questions? Yes.
If there's no extrema, would you give us a problem like that, or like would you just stop, like, or would you build a graph?
You'd still be able to graph it. You would just have to really use the intercepts to help you. Also, you see in our next example, like asymptotes will help us too because we know we have to approach asymptotes. So intercepts and asymptotes will help you if there are no extrema.
Okay.
Okay. Keep going with the concavity though.
All right.
Okay. All right. You're excited. Fine. Alex, what's our domain? Excellent. Logan, why is she excluding -2 and 2? Okay, so we have discontinuities in the form of asymptotes. X equals 2 and x equals -2. Okay, when we look at the end behavior of a polynomial, or excuse me, of a rational function, what do we have to consider? There is a characteristic about our graph that we speak about. Oh, a horizontal asymptote. Where is it?
2.
How do you know?
Because isn't it, if the degree is the same, the numerator over denominator?
Yes. We have an asymptote at y equals 2, so our ending behavior is 2. Yep.
Could you go over the rule about how there's an asymptote? Yeah.
Okay, if the degrees are the same, we look at the coefficients. So we have 2 over 1, y equals 2. If the denominator, like if this was x cubed, it would have a higher degree in the denominator, and our horizontal asymptote would be y equals 0.
I was talking about x equals 2 and x equals -2.
Oh, yes, there's too many 2's up here. Where the denominator is 0, that's where we have vertical asymptotes.
Do you have like a little sheet that you could hand out with all the rules from last year? Because I forgot all of them.
Well, maybe you and I could sit down and write them down sometime. Okay. We're not going to do that. Okay, Jennifer, if we plug in 0, what is our y-intercept? If we plug in 0 for x, what is our y value?
4.
Well, if we plug in 0, we'd be left with -18 in the numerator and -4 in the denominator. Do you agree? Okay. So 9/2? Yeah. Cole, what about our x-intercept? When we set a fraction equal to 0, we're really only concerned about where the numerator is 0.
So, x squared equals 9 plus or minus 3.
Okay, now we need to focus on increasing, decreasing, and extrema. What rule do we need to use to find the derivative? What do you say? The quotient rule. Let's all remember the quotient rule. Hey, we have low, and what is the high?
4.
Okay. Minus high, d low, which is
2x.
all over.
X squared minus 4.
Okay, this is where it becomes very important to simplify. Because we're going to have to take a second derivative. Do you really want to leave it like that?
No,
Didn't think so. So our numerator, we have 4x cubed minus 16x minus 4x cubed plus 36x. Are we okay with that? Okay. So we have these x cubed that cancel, right?
Yeah.
So we can simplify this down to 20x over x squared minus 4 the quantity squared. Ooh. Okay. Our critical points. Josie, where is our derivative equal to 0? Yes. Joe, where is our derivative undefined? Plus or minus 2. I really wish you guys would be nice. Okay, now, on my number line, we already know that x equals 2 and x equals negative 2 are asymptotes. So I'm just going to label them as asymptotes. That way I don't accidentally identify them as a minimum or a maximum. Okay? Whew. All right, so Isaac, W, to the left of negative 2, what does that make our derivative?
I got negative.
Okay, so let me give you some advice here. What's always going to be true about our denominator? It's always going to be positive. So Isaac, I'll let you answer one more time. To the left of negative 2, our derivative will be? Josh, to the between 0 and negative 2, our derivative will be? Remember, our denominator is squared, so our denominator is always positive, doesn't matter.
Negative.
Q, 0 to 2? And after 2, Q again? Okay. Isaac, how many relative extrema do we have? Where? And what is it? We have a minimum. Okay. So we are increasing from 0 to 2 and 2 to infinity. Those are two separate intervals. We are decreasing from negative infinity to negative 2 and negative 2 to 0, two separate intervals. And we have a relative minimum at 0. We've already found that y coordinate. It's 9/2.
Now we find the second.
Yes, yes, we do. Now we have to find the second derivative. Okay. It is important that you get this simplified as much as you can because you have to take a second derivative and you want it to be as nice as possible. Okay, so when we take a derivative of a fraction, we have to use the quotient rule. So, low d high is 20 minus high d low. Chain rule here. Bring the 2 down. X squared minus 4 is now to the first power times the derivative of the inside is 2x. And then we have x squared minus 4 squared squared. So to the fourth. Okay, this is intimidating, but let me give you a trick. Do you notice how there's an x squared minus 4 here and an x squared minus 4 here? We don't cross them out, but we call that a GCF. We can factor it out. We can factor that out. And so then left over would be 20 times x squared minus 4 minus 80x.
So you're gonna just take the 20 and 12 or 20 there.
Yes, yes. Okay, so now what can happen with these? Yes.
Would be 80x squared. Because 220x.
Yep, thank you for catching that. Thank you for catching that. Okay, so we factored out x squared minus 4 to the first. We have x squared minus 4 to the fourth here. So this cancels out with one of these. And we're left with x squared minus 4 cubed in our denominator. Then we can multiply out our numerator. And finally, our second derivative is negative 60x squared minus 80 all over x squared minus 4 cubed. Okay, we're in the home stretch. All we have left is our concavity. Okay, so we know that our second derivative is undefined at negative 2 and positive 2 because x squared minus 4 is still in the denominator. Now we need to know where our numerator is equal to 0. Okay, so if we set our numerator equal to 0, hold on, wouldn't x squared equal a negative 4/3? Can an x squared equal a negative 4/3? It is okay for our numerator not to equal 0. So we're not going to have any points of inflection because the only two numbers we have on our second derivative number line are asymptotes. Okay, now you know how to check for concavity. I'm just going to save us a minute or two and tell you that this is our concavity. Okay, so we are concave up in between our asymptotes and concave down outside of our asymptotes. What? Okay. Okay, we have done a lot of work, haven't we? Put it together. You have all of the calculus in front of you, so help me out. If you have asymptotes, I would draw those in first. We then have some intercepts. We have intercepts at 3, 0, and negative 3, 0. And then we have an intercept at 0, 9 halves. Which also happens to be what? Zero 9 halves is what? Is a minimum. Okay. So, on the interval negative infinity to negative 2, we have labeled that our function is decreasing and that it is concave down. Decreasing and concave down, and we know we have to approach those asymptotes. On the interval 2 to infinity, our calculus told us that we are increasing and concave down, correct? Increasing and concave down. In between negative 2 and 2, our calculus told us that we are concave up. And then our first derivative told us that we are decreasing from negative 2 to 0 and increasing from 0 to 2. So we're concave up, decreasing, increasing. Yes?
If that was a minimum, wouldn't you already know that it goes from decreasing to increasing?
Technically, yes.
So why do we need to find that part for concave?
Because we got to prove it.
Why do we need to find concave up?
Yeah.
Because this is decreasing to increasing. Okay. I mean, since it's a rational graph, you have an idea that that's what it's going to look like, but you need to justify everything. Okay. All right. So here's my expectation. You have, these are the 5 graphs that are required on your assignment. Okay. Now, I want you to at least get through 3 of them tonight. If you have time for all 5, that would be awesome. I'm going to give you 4 more tomorrow. Okay? But you need to come tomorrow with having done some problems. So I'm going to say out of these 5, do at least 3. You're going to have to do all 5 of these, but I'll let you spread it out over the next 3 days. So by the time you leave tomorrow, you will have these 5 plus 4 more. You'll have 9 problems that you'll need to have done by Monday. Okay. Maybe Tuesday. All right, Monday we're going to keep working on this, but you won't have work time on Monday. Okay, so come tomorrow with 3 of these done so that we can have something to talk about, and then know that I'll expect you to do the other 2 along with the 4 I give you tomorrow.
Or we just do it.